Hello, everyone. I'm going to be learning Calculus 3 again. I'm going to be starting directly from where I left off last time. Hold on. Okay. Let me change to full screen. Right. So, last chapter I was learning about maxima and minima. I'm going to read, I'm going to just skim read this quickly and then I will read the last chapter. Okay, so let's see. Equal to f of x and y be a function of two variables that is defined and continuous on an open set interval. F has a local maximum if f has a local maximum at x naught y naught if f of x naught y naught is greater than or equal to all the f of x y values in that open disk. So I guess over here on this point somewhere would be a local maximum, local maximum, and the local minimum would be the entire boundary of this. The graph of z is equal to square root 16 minus x square minus y square has a maximum value when x and y are 0. It attains its minimum value at the boundaries of its domain, which is the circle x square plus y square is equal to 16. Fermat's theorem for function of two variables. Let z is equal to f of xy be a function of two variables that is defined and continuous on an open set interval containing the point x naught y naught. Suppose the derivative of f, partial derivative of f with respect to y and with respect to x and with respect to y each exist at x naught y naught. If f has a local extremum at x naught y naught, then x naught y naught is a critical point of f. Okay, so critical point is where the partial derivative is 0, where both the partial derivative is 0. So critical point is both of them are 0 or either one of them does not exist. Saddle point is when the partial derivative, when there is a critical point, but it's not an extremum. Alright, let me open this first. The second, given a function c is equal to f of xy, the point x naught y naught and f of x naught y naught is a saddle point if both partial derivative with respect to x is 0 and with respect to y is 0, but f does not have a local extremum at x naught y naught. The second derivative test for a function of two variables stated in the following theorem uses a discriminant d that replaces the double derivative of f in the second derivative test for a function of one variable. So d is equal to f of x double derivative of f with respect to x and then with respect to y. You multiply them and subtract it with derivative of x and then derivative of y square. So if d is more than 0 and partial derivative with respect to xx is more than 0, then f has a local minimum at x naught y naught. Then if this is less than 0, then it's a local maximum. If d is less than 0, then f has a saddle point. And if d is equal to 0, then the test is inconclusive. Okay, let's just go to the next chapter. Example 4.41 was an applied situation involving maximizing a profit function. Let me see that example. Four point 4.41, right? This is 4.41. Okay, let's try to do this. I don't think I will get it correct, but let's try to do this anyways. Pro tea company has developed a profit model that depends on the number X of golf balls sold per month. Number of balls sold per month in thousands. And the number of hours per month of advertising Y. Number of hours advertising. According to this function. So 48x plus 96y, okay, Z is measured in thousands of dollars. Maximum number of golf balls that can be produced and sold is 50,000. The maximum number of hours of advertising that can be purchased is 25. Find the values of X and Y that maximizes profit. Find the maximum profit. Okay, let's see. So X is this. Y is this. We have this equation. So I think we need to find the partial derivative. (48x) 96y minus x square minus 2xy minus 9y square. (48) no, this is 0. This is 2y. This is minus 2x. Then with respect to y, yeah, this is 0, this is 96 minus 2x minus 18y. And then xx, this is 0, this is minus 2. Yy minus 18. Then xy uh, minus 2, right? So D is equal to XX and XY and YY minus square minus 2 minus 18 minus and then 4. 2 times 18, 32 more than 0. And then XX, this is less than 0. So more than 0 and less than 0, then f has a local maximum at x0, y0. But we don't know if it's like, we also need to check the boundaries, right? Wait, hold on. We didn't do x0, y0. We need to find the critical point first. D is always going to be more than 0, right? This is what we learned so far. This is always going to be less than 0. So we need to find what the critical points are. Hold on. I'll just copy and paste the above. Uh, so we can add these two. 48 plus 96 is 114. 144 minus 20y is negative 144 over a minus 20. .2. .96 what is 18 times 7.2? 18 times 96 minus that. So over to 16.8. So hold on. 48 minus 2x 7.2 and 16.8. So this is correct. 96 minus 2x minus 18y. 96 minus 2x minus 18y. It is something wrong here. So we have minus 20y is 0. Y is 7.2. I think x is the issue. Twenty-four minus x minus y. It is 96 by 2. 48 minus x minus 9y. Uh, 9 times 7.2 is 64.8. 48. You have minus 16.8. X has to be this maybe. Twenty-four. I think maybe the y is wrong. Hold on, let's get them both to 0. Let's do positive y and positive 9y. Now let's add them. 24, 48, 72. No, we can't add them. We have to subtract them. What am I? It's, hold on. It's 48 minus 24. And then 9 minus 1. Y is 3. X is, this is 3. 24 minus 21 is 3. Now let's try 3 and 21. 3. Yeah, this works. And add. Since these two conditions always hold, any critical point uh, can be a maximum, right? So we need to collect all the critical points. So in between we have 3 and 21, which is within the boundary. Number X cost per sold per month measured in thousand. So 3000 and 21. Now we need to check the boundaries. Intuitively, 0 wouldn't match, right? When the boundary is at 0, we only need to check 50 and 25. Minus 9y square. Now we need to check it out. Wait, actually, let's check these two. And this is h is partial derivative with respect to x, right? So when we place 50 over here, we get minus 26. Nine times 25 minus 177. So what is the critical point here? This is not possible. This is not part. So 321 is the point, right? Twenty-one, three. Uh, yeah, it's 21 and 3. 3 hours, 21,000. And yeah, we plug in 21 and 3 into the equation. We get 648. Uh, so example 4.41 was an applied situation involving maximizing a profit function subject to certain constraints. In that example, the constraint involved a maximum number of cowbells that could be produced and sold in 1 month and a maximum number of advertising hours that could be purchased per month. Suppose these were combined into a budgetary constraint such as 20x plus 4y is less than or equal to 216 that took into account the cost producing the coupons and the number of advertising hours per month purchase per month. The goal is still to maximize profit, but now there's a different type of constraint on the values of x and y. This constraint, when combined with the profit function, is an example of an optimization problem, and the function is called the objective function. A group of various level curves of the function follows. So graphs of level curves corresponding to all this. In figure 4.59, the value C represents different profit levels. As the value of C increases, the curve shifts to the right. Since our goal is to maximize profit, we want to choose a curve as far to the right as possible. If there is no restriction on the number of copies the company produces or the number of units of advertising available, then we can produce as many copies as we want and advertise as much as we want, and there would not be a maximum profit for the company. Unfortunately, we have a budgetary constraint that is modeled by the inequality. To see how this constraint interacts with the profit function, uh, figure 4.60 shows the graph of the line 20x plus 4y is equal to 216 superimposed on the previous graph. As mentioned previously, the maximum profit occurs when the level curve is as far to the right as possible. However, the level of production corresponding to this maximum profit must also satisfy the budgetary constraint. So the point at which the profit occurs must also lie on the red line. Inspection of this graph reveals that this point exists with the line is tangent to the level curve of f. Trial and error reveals that this profit seems to be around 395. When x and y are both just less than 5, we return to the solution of this problem later in this section. From a theoretical standpoint, at the point where the profit curve is tangent to the constraint line, the graph of both of the function evaluated at that point must point in the same direction. Recall that the gradient of a function of more than one variable is a vector. If two vectors point in the same or opposite direction, then one must be a constant multiple of the other. This idea is the basis of the method of Lagrange multipliers.
Lagrange multipliers.
Hold on.
This idea is the basis of the method of Lagrange multipliers.
Why does it disappear? Is there a shortcut for reading aloud?
This idea is the basis of the method of Lagrange multipliers.
Lagrange multipliers. Let f and g be functions of two variables with continuous partial derivatives at every point of some open set containing the smooth curve. Suppose that f, when restricted to points on the curve g is equal to x, y is equal to 0, has a local extremum at point x naught, y naught, and that uh, grad f is not 0. Then there is a number called the Lagrange multiplier for which uh, grad f is equal to the multiplier times grad y. So f of x is our main function and g of x is our g of xy is our constraint function. Set up a system of equation using the following template. Solve for x naught, y naught. It buys this 0. What is g is the smooth curve, right? This being 0. Yeah, why is this 0? So wait, different x and y values. G of x and y is 0. So we are calculating the level curve at the plane, at the x and y plane, right? Where z is equal to 0. Yeah, I think what's happening is instead of this, g of xy is equal to x square plus y square minus 30 minus 10 minus 5. So the level curve is like at one point, right? We get a plane that is like parallel to the xy plane, and the intersections would give a level curve. A y 0 though. If we set this to 0, and we have this, The maximum profit occurs when the level curve is as far to the right as possible. Where is the when this is 400, the level curve is here. 150, the level curve. Hold on. How do I see only the intersection? How do I go left and right? One 50, 0. Okay, so I think uh, so in the original thing, there was a constraint, right? 50,000 and 25. If there was no constraint, you will go as right as possible. As right as possible meaning, what do they mean? Right as possible. So why? As right as possible. Or because the number increases. This number, and let's call it h. How do I add a slider? So as right as possible. Yeah, so it's going that direction, right? Positive x direction. Save no constraint. Bring it to as right as possible, right? Okay. But if we do have a constraint, for example, 220x plus 4y equals 216, we show the constraint here. And then what? Then we try to bring this graph to keep going right. Hold on. 20x plus 4y. How do I not extend this to 3D? Wait, yeah, this would give a straight line. Oh, this is 20x plus 4y. I was thinking of the inner circle. So we move this as far right as possible. Until we hit this. Until the gradient over here matches the The gradient, one of the gradient matches the thing, matches this line. Has a local extremum at point x naught y naught. But if z was different, if uh, wait, this is not 3D. Why am I? This is not 3D. So we have this graph. Need to find the value of a, where this goes to a minimum. But I don't understand. Isn't this graph x, y? Okay, let's just keep going. Golf ball manufacturer Birdie has developed a profit model that depends on the number x of golf balls sold per month, measured in thousand, the number of hours per month of advertising y, according to the same function. And this is the constraint. And so we already have this thing here. No, but wait, we need to find this. Uh, so this grad f g of x naught, y naught, and this is 0. So is it like this? Maybe. I might be wrong in this. Let us see. Is it the addition of these two? This is a vector, this I and this j. Now we need to find this value where it's also 20i and 4j. We already have so in order for grad f to be equal to grad g, this would have to be 20 and then this would have to be 4, right? Now minus 16. Is it 1? No, this is minus 8. So 1, right? Yeah, it's 1. No, it's not 1. Hold on. It's minus 16 minus 24. It's far from 1. So it's 5. And then x 49. No. Yeah, 49. 48, 49, 48 minus x minus 9y is 4. Uh, I don't think this is 49. It's minus 49 maybe. Hold on. 9, 35, 35, 48 minus 45. 4 minus 3 is 1. Hold on. Me. Let me rewrite this. Minus 20. Four minus 5 is negative 1. So x is also negative 1, right? But yeah, got these two. So what? So what now? Y naught 5, x naught is negative 1. Oh, instead of 20 and 4, they wrote 5 and 1. Wait, I did it all wrong. Grad G and this is grad F. And if you set this to 0, where did they get this equation from? You divide each side by 4. Okay, that's where g of xy came from. Uh, you have this. Then they substituted lambda. They simplified to get this. But then they have this equation also, right? So they got y naught is 4 and x naught is 10. Now then they got 540. Okay. Yeah, I did all of that wrong. So g of xy plus 2y minus 7 2x minus 2 and then 8y plus 8y plus 8. 2x minus 2. Write it like this. Two x minus 2, 8y minus 8. You can divide it by 2. You can divide this by 2 since it's a vector. You only need the direction, right? Mm. Now we need to find where I think this is 0. grad f. Where did they get 5 and 1 from? Or like this, right? This is x. No, this is just 1. And with y, it's 2. So this over here. Uh, x, y. Now we need to bring this and this together. X minus 1 is equal to lambda times 1. For my minus 4 is equal to lambda times 2. So, and we have this plus 2y minus 7. Mm, we have this and we have this. Actually, let's subtract them. Minus becomes plus. These two cancel. Minus becomes plus. Minus 1 plus 7. Three over here. Then it will become 4. And y is equal to 2. Uh, 4, 3 and 2. Are we allowed to reduce the vector? No, I don't think what I did was right. This shouldn't be reduced. We keep it like this, then we find the multiplier. And But does not lead to the same thing anyways? Yeah, it does. Two y plus 3. Oh, I see my mistake. It is plus 3. Then 5. 5, right? 5 over here. 5 minus 3 is 2. Now I'm getting 5 and 1. 5 and 1. Right. But how do we know if it's like minimum or a maximum? This part is kind of confusing. In the case of an optimization function with 3 variables and a single constraint function, it is possible to use the method of Lagrange multiply to solve an optimization problem as well. Right, I will just read this. Problems with 2 constraints. The method of Lagrange multipliers can be applied to problems with more than one constraint. In this case, optimization function W is a function of 3 variables. Is subject to 2 constraints. There are 2 Lagrange multipliers. The system of equation becomes this. Let me just read how they did this. Well, here they used 1, right? And here they have 2 constraints. Okay. I'll read more of it on my own. And yeah, I'll end the stream here then. And next stream, I might study operating systems. See what do we have here. Anyways, I will study operating systems next stream. Or I might do some Rayleigh programming. Yes, I will end the stream here. And yeah, see you guys next time. Bye.